Well, it looks like that when I rolled those 4 die 10 times, that only once did I get a 3 of a kind or better. And my question today is going to revolve around that question. What's the probability of rolling 4 fair die and getting a roll that results in 3 of a kind or better? Now, at this point, we can see that it only happened 1 out of 10 times, so it's fairly unlikely. Let's see how we could use R to simulate this particular experiment to get a sense of the relative frequency that would give us an estimate of the probability of this event. So I'll go ahead and open a new script in R, and I'll tile them vertically, and we'll get started by first rolling a die. To roll a die, of course, we just simply sample the first 6 integers, so sample 6 would work. We want to take 4 samples from those first 6 integers, and we want replace to be true. Let's just see if everything's working as it should, and indeed it does seem to be rolling the die 4 times and allowing for repetition here. So that means that replacement true is working as intended. Now the next thing we need to do is figure out how to count the number of, I guess, repeats. So one way we can do that is by inspecting the table of the roll. So if we, well, let's put roll in there so we can inspect the roll as well. So when we run the program now, we see that the roll was a 6, 6, a 4, and a 1, and the table of rolls, of course, is a 1, 4, and a 6, where 6 has been repeated twice. So in effect, what the table does is count the number of iterations of any one face. And so what we'd like to know in the context of our question is, well, what's the maximum in the table of rolls? So let's go ahead and run it again. And I can see that this is counting 4 twice. So the maximum value in the table of rolls is 2 because we got 2 4s. And the maximum amount in the table of rolls now is 3 because we got 3 2s. So it seems like we have a sense of how to iterate it, I guess, in a single roll setting. But what we'd like to do now is be able to do this using, say, 10,000 rolls of 4 die. So in order to accomplish that, one of the things that's helpful is a for loop. So I'll go ahead and set up a for loop. The first thing I'm going to do is set a value n to be the number of simulations. I'll initially set it to 10 just so that it's relatively small. Another smart thing to do when you're using a for loop is to establish a results vector. So a place to put the results that you're going to generate in the for loop. So in this case, the results vector is going to consist of a vector. That's the repetition of 0 n times. So that's just, it's just simply a 1 by n vector that's filled with zeros at this point. Once I have the number of iterations and the results vector established, then the for loop can begin. So for the for loop, sorry about that. For the for loop, I'll start with the syntax for I in 1 to n. So that basically is the syntax of a for loop. You set some sort of an index. This index can be any letter, and I usually use I. And then you begin the body of the for loop with the curly brackets, and you end the body of the for loops with the end of the curly brackets. So what I want you to be aware of is that everything that's within the curly brackets that I have highlighted right now is considered part of the for loop. In other words, it'll be executed 1 to n times, where the index I will range from 1 to n. So for each one of these i's, it'll roll, and I'll go ahead and get rid of the printing of the roll right now, and then it'll calculate the max table roll. The problem is that we want to keep track of all of those max table rolls, so we need to place them someplace, and lucky for me, I have a results vector that I will place the max table rolls in the ith location of that results vector, so that we can keep track of what's going on inside the for loop. So let's just see if it's running right now. So what I'm going to do is have it print roll. So when you're inside of a for loop, the print command is the way that you can actually get it to print for each, I guess, value of I, what the for loop is calculating. So I'm going to go ahead and run it now and see what we get. And we see we get 10 sets of outputs, one for each of the values of I. So when I is 1, it rolls the die and it places a 2 in the first position of the results vector. The reason it placed a 2 there is because there was 2 6s. So when I is 2, we get 3, 1, 1, 3, and we get another 2 placed in there because we got 2 3s and 2 1s. When I is 3, we get 2 2s, so 2 is placed. In the fourth row, we get a 2 because of 2 6s. In the fifth row, we get a 3 because we got 3 6s. In the sixth row, we get a 1 because we got all unique rolls. In the seventh row, we get a 1, all unique. In the eighth row, we get a 1 because of all unique rolls. In the ninth row, we get a 2 because we have 2 6s. And in the 10th row, we get a 2 because we got 2 2s. So now it does seem like it's working fairly well. And we can go ahead and take out the print statements because we probably don't want to see 100 of these lines at this point. And so now I'll go ahead and run it 100 times. And then once I step out of the for loop, what I'd like to see then is a table of the results. When I run it all now, the table of results shows the following results. It looks like that out of the 100 trials, 8 trials, I got a 3 of a kind, and 1 trial, I got a 4 of a kind. So right now we're running around 9% of trials resulting in 3 of a kind or better. Let's go ahead and run it for 1,000 rolls and see what happens. So out of 1,000 rolls, I get 105 3 of a kinds and 1 4 of a kind. So that's about 10.6%, I guess, of the rolls that are resulting in a 3 of a kind or better. But if I run everything again, I'm probably not going to get the exact same result. I can see 96 and 3, so here we're getting about 99.9% of the time a 3 of a kind or better. Maybe what we should do is go ahead and call it a proportion table to let it calculate the proportion in there. And so here I'm seeing about 9.4%. Here I'm seeing, really low there, 71, 78% of the time I got 3 of a kind or better. 95, so about 10% of the time 3 of a kind or better. The fact that we've got such, I guess, variability across runs of the program indicates to me that we should probably up the number of simulations or trials, I guess. This is going to take a little bit of time. Now we're getting that result. Let's go ahead and run it again and see if we have a consistent result. So we're getting a little bit more consistent, but I'm gonna pump it up one more value of 10. So let's run it 100,000 times and let it run. Of course, this will take a little bit of time, and you should be aware of the fact that a for loop inside of a program is going to always cost you more runtime. It's just computationally more exhausting to the computer to conduct a for loop. So you should try to avoid it if you can. And in this case, you can't avoid it, but we'll go ahead and use it anyway. So now we're getting about 0.934, 0.005. Let's run it one more time and see if we have consistency across runs. So I guess just calculating based on the previous result, it looks like it's about to the third decimal place, 0.098, 9.8% of the time, something like that. And in this iteration or this trial, I'm seeing a little bit lower result, 0.096-ish. But we're getting somewhere in the neighborhood of 0.098, 0.096. Fairly consistent, and I'll stop it there. Perhaps if you had more time, you might want to tack one more 0 on there and let it run. This particular program might take up to a couple minutes for that to actually happen. So just be careful when you add extra zeros to your number of trials in the simulation.